Now, on the quiz that's going to be on Monday, I am going to give you the simplified version of our first and second derivative. You'll notice because this was a funky one, I did actually give you some facts that function equals 0 at 1, just so you kind of had that information. Anyway, so the first question says, where does f of x have holes? So the first thing you want to do when at all possible is to get your original function into factored form. So this would be x plus 1, x minus 1. If you take out an x, you're left with x squared minus x minus 2, which factors further to be x minus 2 and x plus 1. So that's the factored form. Now remember, a hole occurs when a factor on top matches a factor on the bottom. So a hole occurs at x plus 1 equals 0 or at negative 1. So the first part of this really is pre-calc stuff. There's nothing, really problems 1 through 6 are all stuff we learned in pre-calc. Where does it have a vertical asymptote? Well, that would be where our remaining factors, that's where our remaining factors are equal to 0. So at 0 and at 2. So the domain then is answered completely from the next part. We have to skip those values in least to greatest order. So we have to skip negative 1. We have to skip 0. We have to skip 2. So you'll notice that our domain skips the hole at negative 1, the vertical asymptote at 0, and the vertical asymptote at 2. Now the x-intercept, if we focus on the simplified version, the x-intercept is where any remaining factors in our numerator are equal to 0. So in this case, it's just where x minus 1 equals 0. The y-intercept, we just plug 0 into our simplified version. If you plug 0 into the simplified version, you get negative 1 over 0, so it's undefined, so there is none. There's a vertical asymptote there. I should have known that. But anyway. Next, a horizontal asymptote or slant asymptote. The one I give you on Monday will not contain a slant asymptote. It's a horizontal asymptote, if it has any. Remember the rules of horizontal asymptotes. Let me go over the rules real quick. If the power on top is more, there is none. If the power on bottom is more, it's 0. If the power lead term degree on top matches degree on bottom, you use the coefficients on the lead terms. The power on the top in the original was 2, on the bottom was 3. On our reduced form, still, no matter what, our bottom has more, so our horizontal asymptote is at 0. So problems 1 through 6 are all pre-calc stuff. That's nothing that we knew that we didn't know already. So you may have to remember, look at those rules or something. So remember, the horizontal asymptote is the comparison of the powers on top and bottom. If the power on the bottom is more, it's 0. If the power on the top is more, there's nothing. If the powers match, so the degree on top and bottom match, just use the coefficients. So now that takes us to critical numbers and increasing and decreasing. Remember, 7 and 8 are all about our first derivative. Now I have given you our first derivative in factored form, or not in factored form, but in reduced form. So the critical numbers are going to be where our first derivative is either undefined or where it is equal to 0. Now, our critical numbers, we already know the critical numbers occur at 0 and 2. We can clearly see our denominator makes it so that 0 and 2 are undefined. But our question is what about that top? Does x squared minus 2x plus 2 equal 0? Well, in fact, unfortunately, it is not a factorable quantity. But we can use the quadratic formula. So if we do the quadratic formula, it is negative b plus or minus the square root of b squared minus 4 times a times c actually gives us negative 8. We can stop right here because this thing here contains an I. So there are no critical numbers except for 0 and 2. Now, unfortunately for us, not necessarily unfortunately, always ask yourself, did 0 and 2 work back in the original function? No, they were asymptotes. So we're just going to put open circles to remind us. Those aren't critical numbers that can be possible maxes and mins. They're not points in our graph. They're just separations in our graph. Those separations can be a separation from, say, increasing to decreasing or so on. Okay, so we've got our derivative, and I know, take a look at it. It's somewhat complicated, but what do we know about an x squared quantity? If we square something, what is its sign? Positive. So both of those bottoms are always positive. We don't have to worry about it. Thank you. So both of our bottom quantities are always positive. So we can include that in a little line if you want. The bottom's always positive. We don't really, it's not affecting our sign. The only thing that's affecting the sign is the top. So let's plug in test values. What happens in this section? What happens here? And what happens here? If we plug in negative 1, okay, let's do that for a moment. It is the opposite of negative 1 squared minus 2 times negative 1 plus 2. It's a negative. A positive times a negative, this section is decreasing. I plugged negative 1 into the first derivative, and I got a negative. And I'm just focusing on the top. The bottom, if we plug in 1, we get 1 minus 2 plus 2, and the opposite of that, just a minute, I believe it is a negative. We get negative 1, so that's a negative. So that's decreasing. And then if we plug in 3, we get the negative of, or the opposite of, 9 minus 6 plus 2, which is a negative. So this function is decreasing, decreasing, decreasing. So how do we write that? Because we do have 3 separate pieces of our graph. So we can say our critical numbers here are at 0 and 2. Our intervals of increasing and decreasing. So it is decreasing from negative infinity to 0, from 0 to 2, from 2 to infinity. Okay, now let's look at number 9. Now, remember, 9 and 10, let's change that color. 9 and 10 are about our second derivative. So now we're going to focus on that derivative. Now, again, we do have critical numbers that are occurring at 0 and 2 again. But this little line right here tells you that we do have something happening at 1. Because the top is equal to 0 at 1, our derivative is equal to 0 at 1. 1 is a point that does work in our function, so something is happening at 1. So now we're going to make a little chart here for our second derivative. 0 and 2 aren't things that work, so note that so that you don't try to include them in anything. 1 is a point that works, so let's actually put a little dot there. I mean, it's a point. It could be an inflection point. I don't know. I'm going to find out. Okay. So this one does require that I do use all the pieces because there's cubes this time. So I'm going to include x cubed and x minus 2 cubed. And then I am going to include that 2 times, would you guys tell me what it says? X cubed. What's that? What's the, what? Okay, never mind, I can see it. Okay. So let's plug in -1, 1/2, 1.5, and 3. Now, let's do the top 2 first because they're the easiest to go. If I plug in -1 and I cube it, I get a negative. If I plug in positives, cube is going to keep it a positive. Now let's plug into the x minus 2, but we got to cube it. If you plug in -1, you get -3. I cube it, it's going to stay negative. If I plug in 1/2, I get -1.5. I cube it, it's going to stay negative. 1.5 minus 2 is a negative. Cube it, it's going to stay negative. If I plug in 3, that's the first one where there's a positive. And do you see how the 0 for that is 2? See how to the left is negative, to the right is positive. Expect some kind of separation and it's 0. That makes sense, hopefully. But this yucky one, let's plug into that. If I plug in -1, I get a negative. 3 negatives make a negative. That section's concave down. Now I'm going to plug in 0.5. If you plug in 0.5, you get a negative. 2 negatives make a positive. That section of our graph is concave up. Let's plug in 1.5. 1.5, if you plug it into that thing, you get a positive. 1 negative is negative. That section of our graph is concave down. If you plug in 3, you get a positive. 3 positives make a positive. That part of our graph is concave up. Now let's put that on the line over here. Okay. So 9 is the intervals of concavity, and 10 is the inflection points. Okay. So our intervals of concavity, it is concave up from 0 to 1, and then from 2 to infinity. It is concave down from negative infinity to 0, and then from 1 to 2. The only inflection point, this has a switch in concavity from up to down. This is an inflection point at 1. And then 11 says to graph it accurately. Now, to graph it accurately, let's note the points we've got. There's a hole at -1 we have to account for. We already found an x-intercept at, do we have an x-intercept? No, we don't. Oh, we have an x-intercept at 1. No, is it the other way around? I'm sorry. 1, 0. Let's see what else we got that we know for a fact. We have an inflection point at 1. Oh, and it's a point already. That's an intercept. That's good. Okay, let's put on everything we know, and then we'll see. The only thing I definitely want to plug in is -1. So I am looking at the simplified version to do this. X minus 1 over x times x minus 2. If I plug in -1, I get -2 over 3. Okay. So let's put our vertical asymptotes at 0 and 2. We know we hit the point 1, 0. At -1, -2/3, put a physical open circle on our graph. Our left end heads to 0. Our right end heads to 0. So what points do I need? I really kind of want to see what's happening for here. Our graph is ever decreasing. Remember that? We got all decreases. So think about, for me to go through this point, I have to keep decreasing. I have to be decreasing. This is concave up, concave down. See how it's ever decreasing, that point of inflection? This is ever decreasing, concave down. See how our cup is down and we're going downward and we're heading toward those asymptotes. So really the only piece I'm super concerned about is what happens to the right of 3. So let's plug in 3. If we plug in 3 to our simplified version, I get 2 over 3, or 2/3. So at 3, I'm up at 2/3. Now that's a real point on our graph. So put that point there. And that tells me I'm sandwiched in this little section. You can see I'm decreasing. I'm concave up. So that is what your graph looks like. It is a function, guys. If you don't know what's happening, plug in some points. Put on your asymptotes first. That's going to really separate. And think about it. Our domain was separated a piece, 1, 2, 3, 4 pieces. Okay. So you have the rest of class. There's a bonus assignment of another video of me doing this again. Do it. That's what I want you to do right now. Work on your 3-5 homework. We can answer questions about that. I have to, there you go.